Infrared spectroscopy and Raman spectroscopy are used to identify the pigments, dyes, and other materials used in these objects, which can help to date them and determine their origin. In recent years, there has been growing interest in the use of spectroscopy for non-invasive medical diagnosis and monitoring. For example, near-infrared spectroscopy, NIRS, is being used to study brain function, and is being explored as a potential tool for diagnosing conditions such as Alzheimer's disease and depression. Spectroscopy also plays a crucial role in the development of new materials, as it allows scientists to study the electronic and optical properties of materials at the atomic and molecular level. For example, the development of new electronic and optoelectronic devices, such as transistors, LEDs, and solar cells, relies heavily on the use of spectroscopic techniques. Another important application of spectroscopy is in the study of biological systems. In particular, fluorescence spectroscopy and circular dichroism spectroscopy are commonly used to study the structure and function of proteins and other biomolecules. These techniques provide valuable information on the folding, stability, and interactions of these molecules, which is important for understanding their biological roles and developing new drugs and therapies. Spectroscopy has also found applications in the study of atmospheric chemistry and climate change. In particular, remote sensing techniques, such as satellite-based spectroscopy and aircraft-based LiDAR, are used to study the composition and properties of the Earth's atmosphere, and to monitor changes in the ozone layer and greenhouse gas concentrations. In recent years, there has been growing interest in the use of spectroscopy for precision agriculture. For example, near-infrared spectroscopy, NIRS, can be used to analyze soil samples and determine the nutrient content, which can help farmers to optimize their use of fertilizers and maximize crop yields. One of the most important applications of spectroscopy is in the study of materials for energy conversion and storage. For example, spectroscopic techniques are used to study the properties of materials for solar cells, fuel cells, and batteries. By understanding the electronic and optical properties of these materials, scientists can develop more efficient and cost-effective technologies for energy conversion and storage. Spectroscopy also plays a crucial role in the study of catalysis, which is the process of accelerating chemical reactions. In particular, infrared spectroscopy and X-ray absorption spectroscopy are used to study the structure and properties of catalysts, which can help to improve their efficiency and selectivity. Another important application of spectroscopy is in the study of surfaces and interfaces. For example, surface-enhanced Raman spectroscopy, SERS, is used to study molecules adsorbed on metal surfaces, while X-ray reflectivity is used to study the structure of thin films and interfaces. Spectroscopy is also used in the study of plasma physics, which is the study of ionized gases. In particular, spectroscopic techniques are used to study the properties of plasmas, such as their temperature, density, and composition. This information is important for understanding the behavior of plasmas in fusion reactors, which could provide a source of clean and sustainable energy in the future. Spectroscopy can be used to study the electronic and optical properties of nanomaterials, and to understand how these properties are affected by changes in size, shape, and composition. For example, Surface plasmon resonance spectroscopy is used to study the interaction between light and metal nanoparticles. While photoluminescence spectroscopy is used to study the emission of light from semiconductor nanoparticles. Spectroscopy also plays a crucial role in the study of quantum materials, which are materials that exhibit quantum mechanical behavior on a macroscopic scale.